All right, here we are again for another AP Biology video. This one is about measuring evolution. Just like a lot of the concepts that we've learned this year in AP Biology, evolution is pretty much the same as it was when you learned it in first year biology, but now we need to go into more depth and usually with more math. And so to start off with, we have to make a kind of a mathematical definition for evolution. Evolution would be the change in allele frequency in a population over time. Remember, frequency just means percentages, right? So the percent of each allele in a population will not remain the same. It'll go up and down as the population evolves. And that, of course, means we can measure it, right? We can put numbers to this, and so we can actually try to put quantitative data to the often qualitative idea of evolution. Now, the equations were come up with these guys named Hardy and Weinberg, which is why it's called the Hardy-Weinberg equations. And basically, they came up with these things, and they're just based on probabilities. There's two equations. The first one, P plus Q equals 1. You'll see what that means in a moment. And then a larger one, P squared plus 2PQ plus Q squared equals 1. Right? And you might notice right off the bat that there's two different reasons for the two different formulas. One of them is about alleles, and one of them is about genotypes. So this would just be the big A or the little a. But then the genotypes would be homozygous dominant, or heterozygous, and then homozygous recessive, right? So there's different situations when you would use the two different formulas, which is what we're going to talk about right now. So first off, we have to get this idea of what how the problem is going to be set up, right? And so Hardy-Weinberg, they basically said that their math is all based off probability. And so for their math to work, we have to have a non-evolving population, right? And so we'll get to this, but this is kind of like a null hypothesis. If we have a large population size, we need to have a large population size. Small populations will have random things happen to them, and that's something called genetic drift, which we will talk about after this video, because this concept kind of leads to that idea. So we have to have a large population size. There can be no migration, right? Because if new organisms come into the area, or some of the organisms that we have leave, then that's going to change our frequencies. That's going to change our percentages. So we don't want that to happen in our non-evolving population. There can't be any mutations. Clearly, that's impossible. But in this hypothetical, purely statistical world, there's no mutations. There has to be random mating, which means that, again, there's no sexual selection, that there's no reason why you would choose one mate or the other. And then that leads to the idea that there should be no natural selection, that there should be no reason why anyone is more fit than anyone else, right? And so these are the 5 requirements, that if all these are met, that there shouldn't be any change in allele frequency. Because again, allele frequencies are just statistics, and if you get rid of all these mechanisms that would change these statistics, then they should stay the same. Again, this is the null hypothesis. Just like in the chi-square, whenever you're doing a Hardy-Weinberg situation, you always start with this hypothesis that none of these things are happening. No change in allele frequency should be measured. Of course, that means that when you go out and you measure the allele frequencies at a certain point in time, and then you come back later and you measure them again and you find out that they've changed, well, you've broken your null hypothesis, and things have evolved, right? And so again, the null hypothesis idea comes up a few times in biology. Now, again, of course, as I might have just been trying to say, this doesn't really happen, right? Like it's impossible to have no mutations, and the random mating and no natural selection would be very hard for a population in the wild to actually like meet these requirements, which of course means that things are going to be evolving all the time. But let's talk about the math, right? So first, we have our dominant and recessive allele. I'm going to go with blue is dominant, red is recessive. And so here I'm going to just randomly create, obviously they're not random now because I planned it, but when I made this, it was random. Right? 10 individuals. Some of them are homozygous dominant, some are homozygous recessive, and some are heterozygous. But one of the things that Hardy and Weinberg basically said was, we don't need to think of them as individuals anymore. We want to just think of them as genes. So let's get rid of the individuals and then kind of throw them into a bucket and call that a gene pool, right? These are all of the alleles that are available to the people in the or the organisms in the population for them to use to have their kids, right? And so this would also represent the diversity of the gene pool. So we have all these alleles. We don't care who they belong to yet. We'll see how this all fits together at the end. Now, here comes the probabilities, right? First is this P plus Q equals 1. So this is just for alleles. P is the dominant allele frequency. So what they said was, if I have this gene pool, what are the chances that if I reach into the gene pool and pull out one allele, what are the chances it will be dominant, right? So again, on the screen, if you have these options that are on the screen, just in right here, of course, what are the chances you will pick a blue dot? And of course, that would be 6 out of 20, which makes it a 30% chance. 3 out of the 10 alleles are dominant. The Q would represent the recessive allele frequency. So again, if I was going to go in and reach for one of these dots on the screen, what's the chances that it would be a red one? And 14 out of 20, because of course it has to add to 20. And of course it also has to add to 100 on the percentages. So if it was 30% in one case, it was 70% in the other. But that is what this is saying, right? P plus Q has to equal 1. 30% plus 70% equals 100%. It equals 1. And of course, this always has to be true. Like in reality, you can't have fractions. There must be 100% of everything all the time because you can't have more than 100%. And if you have less than 100%, you just lost some and you just need to go find it. So the first formula is pretty straightforward. P plus Q equals 1. You just need to remember that P is dominant and Q is recessive. The second one then gets a little bit more complicated, but that's because now we're going to be talking about individuals. We're not talking about alleles anymore. If we want to know the chances of having a homozygous dominant individual, we would have to reach into the bag twice, right? So the chances that I reach into the bag and get a dominant allele the first time is 3 out of 10. But I need to do that again. So what are the chances that I'll reach in there for another? Is 3 out of 10 again. You multiply them because it both has to happen. And so 9 out of 100, right? The P squared would be 9%, right? So if this was a gene pool, we would estimate that 9% of the population would be homozygous dominant, purely on the basis of probability. 9% of this population should be homozygous dominant. Let's go to Q squared, right? Because it's squared because we have to do it twice. So the chances that I'm going to reach in there and get one of the recessive alleles was 7 out of 10, but I need to do it twice. So 49% of the population should be homozygous recessive, according to this probabilities, right? This is Q times Q. Again, that's where the Q squared part comes from. Now, the 2PQ, the heterozygous individuals are more complicated because of another one of the laws of probability. So if I want to get somebody who's a big A, little a, the big A was 3, and the little a was 7, so 21 out of 100. But I could have reached in there and gotten the 7 first and the 3 second, which still makes 21, but this is an OR situation, and OR means to add. So in this case, 42% would be expected to be heterozygous, purely on the laws of probability. And again, that's where the 2PQ comes in. We did P times Q, and then we added them together. That's 2PQ. Now, when we come back to our population that I started with, right, 9% of them should be homozygous dominant. Well, 1 out of the 10, right? 10% of the ones that I created are homozygous dominant. Homozygous recessive was 49%. And there are 1, 2, 3, 4, 5 of those, 50% compared to 49% that was predicted. And then, of course, there was 42% for the heterozygous, and there's 1, 2, 3, and 4 of those, right? And so the probabilities did predict the population pretty well. So of course you could have your population data in the first place and then use that to figure out the allele frequencies and things. Or you can have the allele frequencies and you could know the gene pool, and then you could use that to estimate the genotypes of the population, right? So you can kind of go back and forth depending on what you are doing. So how is this used? How do we actually do Hardy-Weinberg problems? Well, the pepper moth is a very famous example, right? If you remember correctly, there was, in the 1800s, there's these moths, and some of them are dark and some of them are light. And in 1848, 98% of the moths were homozygous for the recessive white allele, right? And this is actually, these are real numbers from real data that was collected back then. And so we want to know the frequencies of the 2 alleles in the beginning of the story, right? And so I always start by putting my 2 formulas, p plus q equals 1 and p squared plus 2pq plus q squared equals 1. I don't know which one I'm going to use yet. I always just like to put this out. This might remind you of my strategy when I do the water potential problems, right? I always want to put everything on the screen, and then I try to fill out what I know and figure out what I don't know so I know where to start. So what do I know? I know that 98% of the moths were homozygous recessive for the white allele, right? So which one of these P's and Q's and Q squareds and P squareds and things represents the homozygous recessive individuals? And that would be the Q squared, right? Homozygous recessive is Q squared. So I know that Q squared is equal to 98, right? And so then if I want to find Q, I have to square root that. Right? Of course, that's the square root of 0.98. And so the square root of 0.98 is equal to, what is it? 0.99. And that's a weird thing about square roots, right? Like when you do square roots of decimals, they get bigger often. I'm not that great at math. Maybe there's an exception to that rule. But in this case, the square root of 0.98 is 0.99. So now I know Q. Right? I was able to start with Q squared, and this is always going to, if you can, Q squared is where you want to start from. Remember, the recessive individuals are very telling. We'll get to that in a moment, right? So I know Q. Now I need to find P, right? So now I need to take that and put it over into here. And so P, of course, would equal 0.01 compared to the 0.99, right? P plus Q has to equal 1. And so then I know that in 1848, 1% of the alleles in the population were dominant, and the other 99% of the alleles were recessive, right? So that's not a lot of genetic diversity, by the way, right? Like at least for this one trait. Everybody is the same for the most part. But still, there is that those variations that are out there occasionally, right? And that's all we need, right? Now, all we need for natural selection is for there to be at least some variation happening. Now, you probably know the story where at this point, the Industrial Revolution starts to really kick in, and the soot that's coming from the factories, it turns the trees dark, right? And so then when we come back in 1895, 95% of the moths are dark. Right? And I don't know if you remember, but in the last slide, it said 2% of the moths were dark before. Now 95% of the moths are dark. And we have the same question here. We want to know the frequencies of the 2 alleles. Now, as I did before, I'm going to start with my formula. 2pq plus that is that. And then I need to look at the question to figure out what I know and where I can start. Now, I use this one as an example because this question is, this has a pitfall. There's a trap in this question, right? Because first, is it talking about alleles or is it talking about individuals? Alleles means we use this formula. Individuals means we use this formula. Now it's asking about the alleles, so I don't think that's what it gave us. It's talking about the individual moths, 95% were dark. The very common thing for students to do here is to say, just like we did before, well, then p squared equals 0.95. But dominant traits aren't as helpful because you don't have to be p squared to be a dark moth, right? 95% of the dark moths includes both of those terms, right? The heterozygous ones are going to make the math too hard, right? And you can't solve for two variables at the same time, so you can't start with the dominant trait, right? This is a huge part. And again, if I'm ever going to try to trick you, this is the way that it's going to try to trick you. By telling you the dominant numbers when you really want the recessive numbers, right? So I guess I could have left that up there. If 95% of them are dark, then that, of course, means that 5% of them are light, right? Still light moths out there. So now we know that Q squared is 5%, right? So that means that Q is equal to, what would it be? 0.22, I believe. I'm going off of work I did before. I might be wrong, but I'm pretty sure that's what it is, right? Then that would mean that P is equal to 0.78. And I got that again by doing that, right? I put the P into that formula, so now I can solve for, I put the Q into that formula so I can solve for P. And now I know P and Q, and that's what the question wanted me to know about the two alleles. And so there's my answer for that one. So now in 1895, 95% were dark, but the alleles are now 78 and 22%, which I'm pretty sure means that I did my math right back in the day, right? And so we have measured evolution, right? We went from 1% dominant and 99% recessive to 78 and 22%. We have mathematical proof that evolution has occurred, right? And so, of course, we're going to practice doing this a bunch of times in a lot of different situations to get used to using the Hardy-Weinberg formula.